Hello, and thank you for joining us. We have come a long way in the last several videos. Let's reorient ourselves. In previous videos, we defined our simulation class, our species objects, and the last several videos have discussed how to specify our genotype-phenotype maps and simulate reproduction. In this video, we will discuss how we can update individual states in the simulation using concepts we learned in earlier videos. We will go over how you can use SPEGG to go through your list of individuals and update their phenotypic values. Before beginning, I need to define what we mean by phenotypes in SPEGG. SPEGG defines an individual's phenotype very broadly. It could, for instance, be readouts from a gene expression array or a language a person speaks. While phenotypes can be conceived of very broadly, there are, by default, 4 phenotypes which SPEGG tracks separately. First, an individual's age and sex are stored in separate vectors by the same names. The DEM or patch to which an individual belongs is located in a vector we call DEM. After all, an organism's spatial location can technically be considered a phenotype. Finally, the vital state of an individual is recorded in a vector we call status. Of course, in principle, you can duplicate the functionality or purposes of these vectors inside your list of phenotypes. For example, you might want to track age since the individual entered a particular life stage as opposed to age since birth. To be sure, doing so is not always necessary. In most simulations, 2 phenotypes you will frequently want to update at every time step are the individual's age and the individual's vital state. For instance, when each individual has a background mortality rate, you would want to update their vital state by drawing a Bernoulli random variable whose probability of success is given by their per time step survival probability, itself, in turn, another phenotype. Similarly, in most models, you will want to increment an individual's age at every time step, or on every nth time step. We should point out, for models that include migration, an individual's DEM should also be updated, but we treat the updating of DEM separately through a distinct migration function. For an example of how the migration function gets implemented, please see the code in the directory examples. Under that, coevolution. But for this video, let's focus on the 2 phenotypes that we have encountered before in our 3rd video introducing the genotype-phenotype map, namely, the individual's baseline fecundity score and their probability of surviving each time step. We will actually delegate the updating of an individual's phenotype to a class we call update behavior. Update behavior is in charge of 3 activities. First, it is used to instantiate a class that will be in charge of updating the set of phenotypes we are interested in updating during each time step. Second, it will actually call a function that will modify each individual's phenotype accordingly. Finally, it will go through your list of individuals and determine their vital states, that is, whether they are dead or alive. Of these 3 functionalities, only the last one is predefined using a general function called determine mortality. What determine mortality does is look for the phenotype that is in charge of keeping track of an individual's per time step mortality probability, and draws a Bernoulli random variable based on that probability. It will then update the individual's corresponding vital state. We won't discuss the function in much detail here. Now we would like to specify the update behavior that is specific to our species. To do this, we will define a class called updateDemoSpecies and define it in a header file by the same name. We'll want to access the members of the base updateBehavior class, whose header file is defined in the species update directory. UpdateDemoSpecies will inherit all the functionality we just discussed from the updateBehavior class. As we saw in the parents class, we'll specify a forward declaration pointer to our species object. Inside this header, we'll define two public member functions. The first is the constructor, which we simply define by calling updateDemoSpecies. The constructor will take as its only argument a pointer to the DemoSpecies object. The next function we'll define in the header file is an update function. Notice back in our updateBehavior base class header file that the update function was a virtual void function. We will actually use polymorphism here to have the update function now carry out operations that are specific to DemoSpecies. When we are all done, these functions will be called by our DemoSpecies class, so we want to keep these functions public. There are also a handful of protected class members to our updateDemoSpecies class. First, just to facilitate code readability, we will create two integer variables called fecundity phenotype index and mortality phenotype index that keep track of the indices for the phenotypes we are trying to update. Second, we'll have our updateDemoSpecies class have its own value of our size argument. With this, we've defined our updateDemoSpecies class. Let's now create a CUDA file for updateDemoSpecies inside the directory DemoSpecies src, which we will call updateDemoSpecies.cu. Let's include the header file we just created and define our constructor updateDemoSpecies. The first thing we want our constructor to do is copy the pointer address from our DemoSpecies instance and store it in species. The second thing our constructor will do is copy the constants. The constant we care about here is the number of individuals alive in our DemoSpecies object, stored in the variable species size. Next, we want to specify the indices for the phenotypes tracking mortality and fecundity. Now that we have specified the constructor to update species, let's define the update function. If you've been following our videos so far, it shouldn't come as a surprise to you that our update function will make use of a thrust functor. Now recall how we invoked functors from video 2. First, we have to define our functor as a structure. So let's go back to our updateDemoSpecies header file. There, we'll define a structure called DemoSpecies updating functor. This functor will update each individual's mortality probability and fecundity as follows. An individual's fecundity will increase by a value of 1 during each time step, so older individuals are more fecund. However, an individual's mortality risk will also increase by 5% during each time step. Our functor will take tuples with two values, the individual's fecundity phenotype and their mortality probability. So, as in our previous examples, we'll call the template to tuple and define an operator function that operates on both the CPU and the GPU that takes as an argument our tuple. Next, we will define our functionality. We'll assume that the 0th item in our tuple is the individual's fecundity, and that the other element represents the individual's mortality. So we will update their fecundity by simply incrementing this value by 1, and then update their mortality risk by also incrementing this value by 5%. This describes a model where during each time step, individual fecundity increases, but so does individual mortality. Let's go back to our .cu file stored in the directory src. What we will do is define an instance of our functor DemoSpecies updating functor, and then call this functor using the thrust for each function we last saw in video 5. As before, we will wrap our two input vectors, the fecundity phenotype vector and the mortality phenotype vector, using thrust make tuple, and zip them using thrust make zip iterator. Remember, the last element of the tuple we want to reference is dot begin plus size. Finally, we will call the instance of our functor's structure demo species updating functor instance. Now we are almost ready to call our update behavior object from our demo species object. Before doing so, we will want to create a CUDA file implementing one of the functions we saw earlier inside our update behavior class. There is a function here called createUpdateBehavior. Of course, update behavior will have to know what this class is, so we will also need to include a header file, updateDemoSpecies.h. We actually have to specify which species update behavior class we are going to call from our update function inside demo species. For our example, there is only one species, so we can define this to always return a new instance of update demo species. Hence, because we have only one species, we are going to just return a new update demo species object. But you can imagine how, in a multi-species simulation, it might be necessary to tell the update behavior which species update behavior object you have to return. In that case, you might have an argument that takes your species ID and, based on the species ID, returns a different update species object. Now that we have thoroughly defined the update behavior, let's actually call this class from inside demo species. Inside update, we will create our pointer to our update behavior object using only the base class update behavior. We will then call our factory method createUpdateBehavior. Next, we call our update function. This code will take care of updating fecundity values by incrementing them by 1 and increasing the individual's mortality risks by 5% during each time step. And finally, we call determine mortality to update everyone's vital states in the simulation. A final task will be left to the viewer. Can you implement a function that will also increment everybody's age by 1? Now, the update functions we discussed in this video aren't terribly interesting or even biologically realistic. But this same basic approach could be used to simulate everything from coevolutionary interactions to complex physiological processes to behavioral interactions. Some of these are available in the main SPEGG repository. In the next few videos, we'll go over how we bring together everything from the last 8 videos so we can finally run our simulation. Thank you for watching, and if you have any questions, please shoot us an email via our mailing list, speg-users@googlegroups.com.